For more than 100 years, humanity believed Jupiter had a clear, solid core, a dense heart of rock and metal anchoring the largest planet in our solar system. That idea was never seriously questioned in classrooms or textbooks because it felt logical, stable, and complete. A massive planet, after all, was supposed to grow around a massive center. But when the Juno spacecraft began measuring Jupiter's gravity with a level of precision no mission had ever achieved before, something unsettling emerged. The data did not point to a compact core at all. Instead, Jupiter's mass appeared spread out, blurred, and partially mixed with the layers above it, as if the planet refused to separate itself into clean internal zones. There is no sharp boundary where solid rock ends and fluid matter begins. No clear line dividing a core from its surrounding interior. What scientists found looks less like a traditional planetary core and more like a gradual transition. A deep interior that cannot be neatly classified by the models we once trusted. This discovery suggests something far more radical than a simple correction. Jupiter may not just be misunderstood. It may be a type of planet that never truly existed in our textbooks at all. A world whose internal structure does not follow the rules we assumed were universal. And if the largest planet in the solar system does not even have a stable, well-defined core, then a troubling question emerges. Are our theories of how planets form fundamentally incomplete? So if Jupiter does not have a core in the way we always imagined, what does the idea of a planetary core really mean? What most of us think we know about Jupiter comes almost entirely from what we can see. And that turns out to be a serious problem. The swirling bands, the giant storms, and the iconic Great Red Spot feel like the planet itself. But in reality, they represent only a thin atmospheric skin. Those clouds are just a few dozen kilometers thick, floating on top of a world that extends tens of thousands of kilometers downward. Beneath that colorful surface lies nearly all of Jupiter's mass, hidden in complete darkness where sunlight has never reached and never will. This is where the planet truly exists, not as a visual spectacle, but as an immense gravitational structure crushing matter into unfamiliar states. Yet, for most of human history, this vast interior remained inaccessible, forcing scientists to rely on surface appearances and indirect clues. Jupiter's gravity complicates the picture even further. It is so strong that it subtly distorts spacecraft trajectories, bends radio signals, and masks the true distribution of mass beneath the clouds. Early observations could only hint at what was happening inside, never confirm it. As a result, the models we trusted for decades were built on inference rather than direct measurement, on what seemed reasonable rather than what could be proven. In other words, our understanding of Jupiter was shaped less by what we knew and more by what we assumed. We projected familiar planetary rules onto a world that may never have followed them in the first place. And that raises an uncomfortable possibility. What if much of what we believe about Jupiter is based not on its true nature, but on an atmospheric illusion? So if almost everything visible on Jupiter is only surface deep, how can humanity ever hope to see what lies tens of thousands of kilometers beneath those clouds? That question is exactly what led to the Juno mission. And it marks a true turning point in how we understand Jupiter. Unlike earlier spacecraft that only skimmed past the planet, Juno was designed to orbit deep within Jupiter's gravitational field, allowing it to measure subtle variations in gravity with extraordinary precision. For the first time, scientists were no longer guessing from surface features. They were directly sensing how mass was arranged inside the planet. What Juno revealed was completely unexpected. The gravitational data did not match a planet built around a small, compact core. Instead of detecting a dense central mass pulling everything inward, the measurements showed that Jupiter's mass is spread out over a vast region. The center of the planet appears diluted, extended, and partially blended with the layers above it, rather than sharply separated from them. This meant that Jupiter does not have a core in the traditional sense. There is no clear boundary where heavy elements suddenly stop and lighter material begins. Rock, metal, and exotic fluids seem to fade into one another, forming a deep interior that behaves more like a gradient than a layered structure. To describe this strange configuration, scientists introduced a new term. They called it a fuzzy core. The idea of a fuzzy core challenges one of the most basic assumptions in planetary science: the belief that large bodies naturally sort themselves into neat layers under gravity. On Earth, heavier elements sink and lighter ones rise, even in simpler models of gas giants. This principle was expected to hold, but Jupiter does not seem to follow that rule, at least not in a way we can easily explain. And that leads to an even deeper mystery. If gravity alone should organize a planet into clear layers, then something powerful must have disrupted that process inside Jupiter. Something capable of scrambling an entire planetary interior on a scale almost impossible to imagine. What force could be strong enough to break the structure of a planet this massive? To understand what could disrupt Jupiter on such a scale, we have to descend into a region where the physics of Earth simply stops working. Deep beneath the clouds, pressure rises so violently that hydrogen, the lightest element in the universe, can no longer exist as a gas. It is squeezed until it collapses into a liquid, not because it is cold, but because gravity leaves it no other choice. On Earth, hydrogen only becomes liquid at temperatures near -250 degrees Celsius. Inside Jupiter, the opposite is true. The pressure is so extreme that hydrogen remains liquid even at temperatures reaching thousands of degrees. Heat no longer causes it to boil. Gravity overwhelms every familiar rule, forcing matter into states that feel almost contradictory to human intuition. This creates something almost impossible to imagine: an ocean of liquid hydrogen stretching tens of thousands of kilometers deep, making it by far the largest ocean in the entire solar system. It is not a surface you could ever stand on, but it behaves like a vast fluid interior, slowly flowing under unimaginable weight. Within this ocean, nothing heavy can remain suspended. Every element denser than hydrogen is dragged downward, sinking relentlessly toward the center of the planet. As material sinks, pressure increases even further, compressing everything below into tighter and stranger forms. The deeper you go, the less Jupiter resembles any planet we know. There is no solid ground, no clear boundary, only continuous transformation driven by gravity. In this environment, stability no longer means balance. It means constant compression, constant motion, and constant change. When matter no longer follows the familiar states we rely on to define planets, the very idea of a stable internal structure begins to blur. And if liquid hydrogen can exist under such extreme conditions, then a far more radical transformation must be waiting below. What happens when liquid hydrogen is pushed even deeper into Jupiter's crushing interior? As liquid hydrogen is forced deeper into Jupiter, pressure reaches a point where even the atom itself begins to break down. Under these extreme conditions, electrons are stripped away from hydrogen atoms, no longer bound to a single nucleus. What emerges is something extraordinary. Hydrogen transforms into a metallic liquid, not solid like steel, but a dense, flowing substance capable of conducting electricity. This metallic hydrogen behaves unlike any material found naturally on Earth. Electrons move freely through it, generating immense electrical currents that flow throughout Jupiter's interior. These currents are not a side effect. They are the source of Jupiter's colossal magnetic field, the strongest of any planet in the solar system. It is so powerful that it stretches millions of kilometers into space, shaping Jupiter's radiation belts and dominating its cosmic environment. What makes this even more remarkable is scale. Metallic hydrogen is not a thin layer or a small core. It occupies a vast portion of Jupiter's interior, making up a significant fraction of the planet's total volume. The deeper you go, the more the planet becomes defined not by rock or gas, but by this electrically active metallic ocean, slowly churning under crushing gravity. But metallic hydrogen creates a serious conceptual problem. Liquids do not form sharp boundaries. They flow, mix, and transition gradually into whatever surrounds them. If Jupiter's interior is dominated by a conductive metallic fluid, then the traditional idea of a solid core sitting cleanly at the center begins to collapse. There is no obvious place where metal ends and rock begins. No clear surface that could be called a boundary. This blurring of states forces a fundamental rethink. If metallic hydrogen and heavier elements like rock and metal are mixed together deep inside Jupiter, then the planet may not have a core in the way we have always defined one. And if that is true, then the very concept of a planetary core may need to be rewritten. If metal and rock can exist as a continuous mixture, does a planetary core still exist at all? One possible explanation for Jupiter's blurred interior points back to a violent moment in the early solar system. Scientists have proposed that a massive rocky body, perhaps 10 times the mass of Earth, may have collided with a young Jupiter while it was still forming. Such an impact would have released an almost unimaginable amount of energy, enough to tear apart a solid core and scatter its material throughout the planet's deep interior. This idea helps explain why Jupiter's core appears stretched out and mixed rather than compact and well-defined. A collision of that magnitude could have disrupted the normal layering process, injecting heavy elements upward and blending rock and metal into the surrounding metallic hydrogen. In this scenario, Jupiter's fuzzy core would not be a failure of gravity, but the fossilized aftermath of a planetary catastrophe. At first glance, the collision hypothesis fits remarkably well. But when researchers attempted to recreate this event using detailed computer simulations, a new problem emerged. In most models, even after a massive impact, the planet's interior gradually settles back down. Over time, gravity reorganizes the material, allowing a distinct core to reform at the center. Yet Jupiter's core has not done this, even after billions of years. This contradiction leaves scientists with an uncomfortable gap. If a collision occurred, it should not have erased Jupiter's core permanently. And if no collision took place, then something else must be responsible for preventing the planet from ever developing a clean internal structure. Either way, the standard story begins to break apart. The possibility remains that Jupiter did not simply form, collide, and recover like other planets. It may have followed a far more unusual path from the very beginning, one that allowed its interior to remain mixed and unresolved. If a single catastrophic impact cannot fully explain what we see today, then we are forced to ask a deeper question. Could Jupiter have formed in a way that is fundamentally different from everything we thought we understood about planetary birth? As Jupiter's internal mysteries deepen, an even more unsettling idea begins to take shape. Jupiter may not fully belong in the category we casually call a planet. With a mass just shy of the threshold required to ignite into a brown dwarf star, Jupiter sits uncomfortably close to a different class of cosmic object. It is massive enough to dominate its surroundings, yet not quite massive enough to shine like a star. What makes this distinction even blurrier is energy. Jupiter radiates significantly more heat than it receives from the Sun. This excess energy comes from deep within, released slowly as the planet contracts and its interior continues to evolve. In that sense, Jupiter behaves less like a passive planet and more like an active object with its own internal engine, quietly glowing from the inside out. Its internal structure reinforces this ambiguity. The presence of vast layers of metallic hydrogen, the absence of a clearly defined core, and the immense magnetic field all resemble processes more commonly associated with stellar physics than planetary geology. Jupiter appears to occupy a transitional state. Not fully a star. Not entirely a conventional planet, but something in between that challenges the categories we rely on. This raises a fundamental problem for astronomy. The definitions we use were designed to describe simpler worlds like Earth or Mars, not extreme objects that blur physical boundaries. Jupiter forces us to confront the possibility that our classifications are conveniences, not truths, and that nature does not care where we draw our lines. If Jupiter exists in this gray zone between planet and star, then it may not be a rare anomaly. It could be the most visible example of a much broader class of objects scattered throughout the galaxy. And if that is the case, a far more unsettling question emerges. What happens if Jupiter is not unique, and the universe is filled with worlds that defy the very definitions we use to understand them? In the end, Jupiter reveals something far more profound than the structure of a single world. It reminds us that nature does not follow the diagrams we draw or the categories we rely on to feel secure. The universe does not organize itself to match our expectations. It simply exists, complex and indifferent to the names we give it. What we call physical laws may not be universal rules carved into reality, but simplified descriptions shaped by the limited examples we happen to observe. Jupiter exposes how fragile those assumptions can be. The largest planet in our solar system, the one we thought we understood best among the giants, still refuses to be fully explained. Yet this uncertainty is not a failure of science. It is its greatest strength. Science advances not when it pretends to have final answers, but when it has the courage to admit what it does not yet understand. Jupiter stands as a reminder that knowledge grows at the edge of confusion, not in the comfort of certainty. When we look up at Jupiter in the night sky, we are not just seeing a relic of the past or a familiar neighbor orbiting the Sun. We are looking at the boundary of our own understanding, a massive question mark hanging quietly in space, daring us to keep asking deeper questions. And if a world as close and well-studied as Jupiter can still defy us in this way, then one final question lingers in the silence. How strange must the worlds beyond our solar system truly be?